Hello everyone, I am Abida Sultana, a PhD student from University of Louisiana at Lafayette. Today I am going to present ELAS, Design and Analysis of Completion Time Agnostic Scheduling for Distributed Deep Learning Cluster.
Deep learning is widely adopted with the recent advances of neural network technique. Many applications of various fields like speech recognition, natural language processing are using the deep learning. Many tech enterprises such as Microsoft, Amazon, Google are providing large-scale GPU cluster facility for training the models. From a statistic of Microsoft GPU cluster, we came to know that the number of DL job training has increased more than 10 times within a year. Also, the GPU cluster size increased 5 times that year. Regardless of increasing GPU number, the usage of hardware is only around 50%, which leads to a huge scope of improvement in designing the GPU cluster manager. Now, the question is how efficiently we can manage GPU cluster for training deep learning jobs so that the utilization as well as user satisfaction are ensured. The cluster manager needs to take care of certain things while scheduling deep learning training job, such as addresses the unique characteristics of deep learning jobs, which will be discussed in the next slide. Avoids the head of line blocking. Multiple requests come at the same time from different users with certain resource demand. With resource demand, we means that the number of GPU a job needed to complete the training. Cluster manager has to serve each demands in minimum time without blocking the other in the job queue. Ensure better job to resource fit. Cluster manager must ensure better resource fit for each job so that when there are multiple resource options available, it can select the best one. It also has to take care of job efficiency as well as better utilization of resource at the same time. It has to take care of user satisfaction by minimizing average job completion time, reducing queuing time, as well as
Now we will discuss some unique characteristics of deep learning training model. Deep learning training model are computation and resource intensive. Special hardware GPU is needed for training the job efficiently. Heterogeneity in model and data size. Each job is different from other because model and data of various size used for training. The model size depends on the layers parameters used for training, and usually large model with huge data need more GPUs and longer training time. Unpredictable training time. Due to the unpredictable loss of the model while training, it cannot be known when the model will converge and the training will finish. Again, many job is terminated before completion while training due to the bad performance of the model. Placement sensitivity. Some models perform better if they can be consolidated in GPUs with fewer number of machines because it facilitates the models with less communication time. Some models are not sensitive to this placement. Let's see how the GPU cluster manager works. Users' requests come with certain demand of GPUs stored in the job queue. The scheduler of the cluster manager decides which job to schedule first based on its scheduling policy. The placement scheme decides where to allocate the job by satisfying its demand. The scheduling and placement policies are determined to serve mainly two objectives: minimizing average job completion time and maintaining high resource utilization. Let's talk about the challenges GPU cluster faces while trying to minimize the average job completion time. Deep learning training time cannot be known beforehand. Some works try to predict the job completion time based on the loss curve, but the loss curve of deep learning training job is not smooth, so prediction is not possible. Some application like AutoML terminates jobs before completion because of the poor performance while auto-tuning the hyperparameter. From Microsoft job trace, we came to know that 32% jobs are killed or finished unsuccessful due to the failure. So we can say that unpredictable training time is a challenge for cluster manager. The second challenge for cluster manager is aggressive consolidation. As we mentioned earlier, not all jobs are sensitive to the consolidation placement. The consolidation of jobs in fewer GPU may save communication overhead, but it may cause longer queuing delay. In this picture, a job requested for 4 GPUs, but it cannot be allocated even if there are 4 GPUs is available in different machine because it is waiting for one machine to be available for GPUs. There is also the possibility of interference if multiple jobs are consolidated in the same machine. Some existing solutions are based on profiling, which determines which job is sensitive to placement consolidation and which job is not. By addressing the challenges, we proposed the cluster manager ELAS with the objective of minimizing average job completion time without prediction. We take scheduling and placement decision without any prior knowledge from the users. Also, our scheduling scheme is a preemptive scheduling, which means each job will get a fixed amount of time once scheduled, which is called service quantum. It also avoids the profiling overhead. The available information we used for ELAS is the number of GPUs and total number of epochs which are submitted by the users upon the submission of job request. The executed service time refers to the time a job has already run, and the executed epoch number is the total completed epoch number a job has finished. With this information, we calculate the priority of the jobs. For job I at service quantum j, the priority of a job is determined by this equation, where this term refers to the resource attained by the job within j service quantum, and this term refers to the epoch progress rate, which is the number of completed cumulative epoch with time, and these terms refer to the remaining epoch number at service quantum j. So we prioritize those jobs which are having less number of epochs, less number of resource, and which has higher epoch completion rate and which has minimum remaining epoch number. Let's see an intuitive example where 3 algorithms are compared based on average GCT, shortest remaining time first, 2D LAS, and ELAS. Shortest remaining time first used the duration of the jobs. For this reason, it got the optimal average GCT. So 3 jobs is requested, and the information used by SRTF is the duration of the jobs, and 2D LAS, which is an algorithm proposed by a state-of-art work TIRCS, it used the information of number of requested GPUs and the executed time of the jobs, and our ELAS used the information of number of requested GPUs and the total number of epoch. So from the result, we see that our algorithm performs better than 2D LAS and near to the optimal one. Also, by theoretical analysis, we have showed that mean response time of ELAS is less than the mean response time of foreground background scheduling policy, which is also a preemptive scheduling policy and has similar scheme. As we talked earlier, over-aggressive consolidation of a job leads to a resource fragmentation and higher queuing delay. In Tyresias' paper, authors represented the fact that consolidation will improve the performance of the job only if the tensor size or the message size of the models are highly skewed. If larger tensors are consolidated, the network contention will harm the performance of training. Now, for knowing the tensor size of a deep learning jobs, one needs to observe the network communication to capture detailed metadata such as message size. This might introduce interference and an extra overhead for cluster manager to take the placement decision. So the question is how to place DL jobs avoiding profiling overhead and without hurting the performance. In ELAS, we have proposed rather a simple and easy solution similar to the scheduling scheme. For some early service quanta, the cluster manager will monitor the progress of deep learning training by placing the job with consolidation and without consolidation scheme. And based on that, it will take decision which is if we want to place the jobs adopting consolidation method or without consolidation method. So this is how the ELAS cluster manager work. The user will submit the job request with various resource demand. The scheduler and placement selector both take the decision based on performance evaluator. The performance evaluator will prioritize the job based on the equation we have discussed, and based on that the scheduler will schedule the job and placement selector will find a suitable place for that job. Let's see some comparison among the prior solution of GPU cluster. ERCS, which is used in Microsoft GPU cluster, does not use any prior knowledge, neither Gandiva and Tyresias, but Optimus predict the job completion time and based on which it makes scheduling decision. ERCS, Gandiva and Tyresias does not have any runtime performance evaluator, but Optimus in runtime calculate the loss rate and based on which it takes decision. And Yarn and Gandiva does not has any objective of JCT minimization, which is opposite to the Optimus and Tyresias. And for placement scheme, Yarn always tries to consolidate the job in fewer GPUs. Optimus is used a capacity based placement scheme, and Gandiva tries to minimize the load, and Tyresias take placement decision based on profiling. Compared to these GPU cluster managers, our ELAS does not use any prior knowledge while taking decision, and it has runtime performance evaluator which calculate the epoch progress rate of each job, and our objective is both JCT minimization and better GPU utilization, and for placement we adopt the performance based decision. Our experiment is conducted on a simulated Java based environment, and the job trace we have used is from Microsoft production cluster where there are 480 jobs with a combination of various requested GPUs. The job follows Poisson process of arrival with an interarrival time of average 30 seconds. The epoch completion rate and the job size are pulled from three different distributions, which is Gaussian, Poisson, and exponential distribution. We compared the performance of four scheduling algorithms, ELAS, Tyresias, SRTF, and Yarn, where SRTF is the theoretically optimal one which used complete job information. We showed the result by the fraction of completed job with respect to average job completion time. The results are simulated on 9 different combinations of 3 different distribution on epoch progress rate and job size. From the experimental simulation of our cluster manager, we found out that ELAS performs 10 times better than the production based algorithm YARN and 1.5 times better than the state of art Tiersias. The result on GPU utilization shows that YARN performs best for the GPU utilization, but ELAS is almost aligned with the state of art Tiersias. We also managed to reduce the queuing delay of ELAS compared to the Tiersias and YARN, and we are showing the result of queuing delay here based on the job trace we used. In summary, our proposed ELAS is a cluster manager for distributed deep learning job which minimizes job completion time without any prior information, and the placement scheme is simple which avoids the overhead of profiling. Also, the performance is better than the existing solution. That's the end of my talk. Thank you.